Microsoft RPC socket activation. My name is Volker Lendecke. I work for SerNet. I've been mentioned in Ralph's talk just a few minutes ago, so I'm a member of the Samba team for quite a while now. And in the recent months, I have started a more personal project to pursue what was triggered by a customer. A while ago, a customer with a proprietary SMB implementation asked us at SerNet to help him with listing shares on his SMB server. And I will show you what listing shares on an SMB server right now means. This customer has an SMB or rather SMB2 implementation, but they didn't want to mess with RPC. And so we helped him with Samba's RPC server that provided the Unix socket for him to connect to, just to be able to list shares initially. Later on, SAMR and LSA also were served by this, but this gave me the insight that we could do the same in Samba, which is really split up the SMB implementation and the RPC implementation. And this is, as I said, it's an experiment. I will show you what this is about, and I will show you the state of the code in a few minutes. So, what is MSRPC? Microsoft RPC is an extended version of the distributed computing environment remote procedure calls. And as you can see on dcrpc.org, this RPC flavor, I mean, there are a lot of other RPC flavors in general. This is most commonly used to interact with Windows services. Although Windows these days has many more protocols than are RPC based, much of the basic infrastructure that Microsoft implements in Windows still depends on the MSRPC protocols. The most prominent these days is Active Directory multi-master replication. This is something that Metz has initially dissected for Samba and implemented, but also things like remote workstation management, remote printing, and even listing shares depends on MSRPC. So now you look at the SMB2 specification and you say, how hard can that be? And you implement your initial calls to open files, to close files, and your artificial tests work. And then what you do is you connect to your server with Windows. And this is a Wireshark trace. Everybody should be aware of this. What you see is that, can you see my mouse here? Oops. The first packet in this Wireshark trace, Windows opens a file to server service. And what you don't see here, it's a file that is being opened on the IPC $share. And what it then does, it does a bind call, a dcrpc bind call. And I will speak about that a lot more in the later slides. And then the real request to open, to list shares, that's what Windows usually does when you connect to it, to a file server, is this netshare enum all request that you really have to implement just to see shares. I think NumJ has suffered a lot to implement this. Everybody kind of suffers a lot to implement this because it's really a protocol that is, for this little task, way too complex. So SMB is just a tiny part of the full Windows experience. Yeah, you try with Windows, you can't see your shares. And listing shares used to be easy in the early days. I hope somebody has looked at MSREP. This is an SMB1 protocol. Samba implements this as part of the landman.c file. It comes from OS2. It also is a bit difficult to encode and decode, but it's really simple calls. It has many limitations like buffer sizes. It comes from OS2. It's not sufficiently flexible to act as a general RPC, remote procedure call, that is flexible enough to serve multiple services. And I think it was with Windows NT, Microsoft decided to use DCRPC and extend it, and probably just to add more transports. Maybe Tom can comment on this, to add more transports to the DCRPC engine, to be able to do general remote procedure calls over any transport. So what does this RPC call look like? When we look back at the Wireshark trace that I've shown you 2 slides before, the first call is we open a server service file. What is it? In the Microsoft world, this is a named pipe. And if as a client, you open this server service file, you open a socket, essentially in the Unix world, you would call that socket, to some server process on the server that you connect to. And in the end, it's not quite, but almost like just a raw TCP socket. You can just transmit arbitrary data. Although it looks like opening a file, it is not. It's just a pipe. It's a transport for arbitrary data. DCRPC also works over direct TCP. But when Microsoft chose our DCRPC, TCP/IP was not really around everywhere. And if you look back, SMB worked over IPX and even NetBEUI. DCRPC is defined over UDP, but to be honest, I haven't seen it myself yet to run DCRPC over UDP. So the first step is we open server service, we essentially connect to a socket, and then we write into the server service handle. This is an RPC bind. And part of this first packet that we send into the server service file, or named pipe, this specifies which exact service we want to connect to. So let me interrupt. I want to let Bartlett in. Somehow I'm host here and I get the messages, Andrew Bartlett wants to enter the talk, which is very nice. Hey, Andrew.
I already clicked and let him in, but yeah, when you're a speaker, you get to be co-moderator as well, so the screen share and everything works. So just ignore the messages.
Hello, Andrew. So the SMB2 write that we saw is the RPC bind, which says, okay, I really want to talk to the RPC service that lists shares. I want to talk to the RPC servers that lists users or translates names to users and so on. And with this packet, we typically also authenticate and we negotiate all sorts of crypto. The next requests then are pure request response, and they are transmitted via SMB2 IO controls, but that's just an implementation artifact. And then the real meat is the netshare enum request that will then list shares. RPC over TCP is of course a lot simpler. That just transmits raw packets, which are here encapsulated in the SMB2 read-write IO control. The Samba RPC implementation, it started in mid-90s. If you Google for Luke Kenneth Casson-Leeton DCRPC over SMB, you will still find a book where when you read the first sections of it, you really start to think how many layers can you put on top of each other to just get RPC done, and how many layers of fragmentation and defragmentation can you get. But yeah, that's the basis where Samba started from. This book essentially came from Luke working on this. And if you look at RPC today, RPC is, if you look in Wikipedia, normally you have something like an interface definition language that defines calls and how to encode these calls and how to decode the answers, the replies and so on. And we did all this in hand marshalling, and this was also one of the questions that we had with the in kernel SMB server, do you do a hand marshalling or is that automated? And yeah, in 2000, Android Trivial started PIDL, which is the Perl-based IDL compiler. And this is what we use these days to encode and decode the RPC packets into really high-level C structures. The difference to the DC RPC IDL compiler is, of course, I mean, functional-wise, we have differences. We do some things they don't do. We don't do some things they do, but it's enough for us to implement what Windows needs. The main difference is the C code you get out of it is actually readable. In the mid-90s, or even when Trig started to do PIDL, these IDL files were completely secret. So we really had to guess. And if you look at our IDL files, the definitions for the RPC calls, you'll still see some unknowns here that we could just now download from the Microsoft website and just fix them. The IDL files were really a big part of the EU versus Microsoft case around 2005 or so. And we essentially, the Samba team was part of that case and made Microsoft see the light that documenting protocols is actually a good thing. And since that case was done, Microsoft fully documents their IDLs, which is great. Thanks, Microsoft. So how are these RPC servers right now implemented in Samba? And I'm only talking about the Source 3 version. The Source 4 version structurally is not really different. It's just not linking into smbd, but into the Samba process. But yeah, that's the same thing essentially. Right now, all our RPC servers are linked into our smbd binary. This is easy, but it's not the right thing to do. And in 2010, Simo Sorges started to spread out spoolss SD. And Andreas told me that this was also to be done for LSA. And I just thought that spoolss SD was the most important one. I'm not sure about this. What we have right now is we have for several RPC daemons or RPC services, you are able to run these services in separate processes. And this structure gets it right. It's just a transport. So SMB in this case is just a transport for the SMB traffic. And what Simo did was just separate this printing into a daemon of its own. And yeah, the RPC's traffic. So RPC traffic, if you look at the Wireshark trace, comes in via SMB. And this is implemented naturally by smbd. But if the spoolss service is then implemented by spoolss daemon, another process, we need to get the data across. And we do this with the Unix domain socket. Yeah, and this talk, the work that I present here is builds upon Simo's work, also on Samuel's work, also on Metz's work. So it's just a continuation, standing on the shoulders of giants. And the work that Simo has done is he forks smbd, but these are only separate processes, but they are still linked into user sbin smbd. And I wanted to split this up. Demo time. So stop sharing. Share screen. Now share my terminal here. Can you see my terminal well?
Yes, works perfectly.
Great. What do we have here? Okay. We have an smbd. And if we look at our smb.conf, it's basically empty. So very, very simple smb.conf. And this smbd just sits there, runs, waits. It listens on port 445. Here we are. And if I now do the following, I want to list shares the way Windows does it. surprise, I get tump. And now I have to be a bit quick. What do we have here now? This smbd has grown some children. I mean, not process-wise, but it has some assistance now. And if we wait a bit, it's gone again. What is this? These are the named pipe helpers that implement the RPC services. And to be able to catch them while they are running, what I'm going to do is I open an RPC client, which keeps this connection open. It is a net share. That essentially does the same. So going to a different window. Nothing yet. This is just the smbd serving RPC client. And if I issue my net share enum all, I get my shares. And now I have my RPC daemons. And let's take a look what this is. Let's first look at this parent here. So this lists the open files of the parent that was forked, that I called Samba RPC daemon. And what you see here is that this guy has a lot of sockets open. And anybody having looked at the Samba implementation will remember these sockets. And these are unique sockets that this process listens on. If we now look at this process doing the RPC, being called RPCD classic, the idea here is that this process really doesn't have any socket open. The only socket that this one has open is the last one here, but this is not a listening socket. This is just the transport socket for the server service. Okay, these processes are still around. If I leave RPC client, and in this case, wait 10 seconds, these processes will be gone. Let's go back. I will come back here in a minute. Okay. We have seen a few processes here. The first one is what I called, and this is really not finalized. I mean, I discussed this with Metz and Ralph. This is what I call Samba RPCD. This is essentially the inet daemon or system daemon or whatever for the Samba RPC daemons implementing the actual services. What it does, it listens on behalf of the RPC server implementations that do the real work. And what we have is we have a number of processes defined. The first one I mentioned here is RPCD endpoint mapper, EP mapper, implementation of the DCRPC endpoint mapper protocol. Then, of course, CMOS spoolss daemon in a separate binary. Then, yes, winreg is a separate binary. And then we have RPCD classic that implements just everything else that didn't fit or that wasn't needed to be put into a separate binary. For example, the RPCD winreg, I needed to put that in a separate binary just for recursion reasons, and I can, maybe not in this talk, but that's really a technical detail, but there were technical reasons to put the winreg service, the registry service into a separate binary. And what this means is that the smbd doesn't have any RPC server code anymore. It just opens named pipes and executes Samba RPCD on demand. That's all it does. Let's see. If you look at has been smbd And if you look at our library for the RPC server loop, it's called RPC server loop. And we actually define a library called libsamba-rpc server loop. And if you look at what smbd links in, I mean, there's a lot. But if I grab for RPC, there is no RPC anymore. And if you do that with a standard master smbd, you get all the RPC services into smbd. This is gone in this implementation. Okay, stop here again. Okay, so how does all this work? A client comes in and wants to open server service. Then smbd tries to open the Unix domain socket that you have just seen that the Samba RPCD listens on, Samba DC-RPCD listens on. The smbd won't see anybody listening there. It gets an access denied or a whatever connection refused. And what it does, it forks and executes this Samba DC-RPCD binary. That then does the following. It asks every RPCD that it can find about the interfaces that it implements. And here's a sample. I will show you that in the terminal in a minute. I call RPCD winreg -- list interfaces. And what it does, it lists the GUID for the interface, including version, the name of the interface, and now we are coming into the terminology, the endpoints or binding strings, or after having looked at that for a while, I can't really get my head around these names. Essentially, these 3 lines with NCACN something define the sockets to listen on. That this RPCD winreg daemon wants the parent DC-RPCD to listen on its behalf on. What the parent then does, it listens on all sockets for the RPC implementation on behalf of them. And when a client connects, the corresponding RPCD implementation forks and execs the server implementation. And when the client has connected, then the Samba DC-RPCD completely hands off the connection to the worker and is done with it. And let's take a look again. So these are installed all in libexec. And Samba. And what you see here is all the RPCD implementations that we implement right now. And let's do this call with libexec Samba RPCD _ winreg -- list interfaces. And we get exactly the string that we had before. And now if I ask RPCD classic, for example, list interfaces, there's going to be a lot more because it does all the stuff that didn't fit into a separate binary. It does server service, it does LSA, it does DS setup, and so on and so forth. By the way, what you see here is it does not do netlogon. It will if I set domain logons equals yes, domain master equals yes. If I configure ourselves as classic domain controller, we should see netlogon here. Hey, we have netlogon. Great. So now this RPCD classic is aware, hey, I am a domain controller. I should implement the netlogon interface. Okay, if I now just directly start, one thing. Let's open the RPC client again. Let's make it spawn the RPC daemons. Oops. -P1349. And if you look at the listening sockets, let's go down to the listening sockets. Hey, tons of files, tons of files. Here we are with the listening sockets. What you will see here, we only listen on named pipes. And that's correct, because what we have configured is a normal classic domain controller, as we have had it before. And the normal classic domain controller for us in the Samba 3 world, or in the classic domain controller world, which is deprecated, we don't really do TCP-based RPC services. And the other mode that you can start your, so the way that is run is if we look at the, if you look at that file, at that process, you will see this named piper here. So named pipe helper. This means that we only listen on the NCAC and NP transport. We can do that differently. We can just start this guy on the command line. libexec samba dc rpcd minus exec rpcds. Okay, this libexec rpcds tells him, hey, please do a list on the libexec subdirectory and look for all rpcds. You can specify individual rpcds here. And if we now go and look what this guy here listens on, 373, and we go down to the bottom to the listening sockets. Now you see, hey, we listen on all these TCP sockets as well. And now we also have the endpoint mapper, which is port 135. Great. So this is now even independent of smbd. I killed the smbd. So what we now have, we have a pure daemon that listens on RPC RPC ports and really spawns and execs the RPC helpers on demand. Let's try. And this is the part that I didn't test. Let's look or NCA EPM map or EPM lookup. So what did this do? I told RPC client to connect to our internal ncal RPC, which is the local Unix transport. And I told it to do an EPM lookup, which is just listing all services via the endpoint mapper protocol. And yeah, we have all these services, which is great. And I just forgot how to do this over TCP syntax-wise, so I don't do that now. But it also works over TCP. Yeah, two modes of operation. This one here is Samba DC RPCD just listens and hands off handling all the connection data or all the connection traffic to the RPCD implementations. Now let's look at the RPCD implementations. They have two modes of operation. Minus list interfaces just shows what services are provided, just for the parent to listen on. If we don't give them these list interfaces, what it does, it just demonizes itself and listens on messaging style, SMB control messaging style messages from their parent for new sockets. These RPCD implementations don't have to care about listening on sockets and so on. Every process, and this is based on Simo's and of course Samuel's work, every of these daemons can handle multiple RPC connections. And yeah, when a client disconnects, what the helper RPCD, my RPC endpoint mapper and so on, do they report the number of connections they currently have to the parent. So the parent always knows how many client each process serves. I can show you that. So I always get that wrong. LSA query. Let's do a bit of calls RPC-wise. EPM lookup, net share. Just let's fire up some of these services. What we have is we have smbd, and we have one RPCD endpoint mapper, and we have our Samba DC RPCD that used to sit there waiting for connects. In SMB control, on the RPC dump status. So this will dump status, oh, RPCD classic, its process ID 1401, it has 2 connections, and the endpoint mapper is 1405, it has 1 connection. Then let's look at this one, the RPCD classic. It has 2 named pipes over for LSA and for server service. So this is what it got from the parent. Endpoint mapper. This implementation for the endpoint mapper completely changed from what we used to have. In the current master code, what we need to do, every RPC service registers itself using EPM insert. Here, I mean, the parent knows everything and it just fills a TDB. And yeah, RPCD endpoint mapper just queries and walks this TDB. That's all. So right now, I just deleted the EPM insert and delete from this because for our implementation, this is not right now not relevant. We don't really have the fancy object-based RPC yet, and then it will become relevant if we do that, ever. Association groups. And this is the last part of my talk. What's an association group? And part of this whole exercise was an exercise in me understanding what an association group is. It's one of the aspects of DCRPC that we so far didn't really get right, but this implementation, I think, solves it. If you look at the, better don't look at the DCRPC spec, you will be more confused than before. An association group essentially is essentially a number space for policy handlers, which from our perspective are just pointers to server-side objects that a client can refer to. You, for example, have an open user, you get a policy handle. This policy handle just refers to the server-side representation of a user over SAMR. These policy handles can be shared across multiple RPC connections. And the way in source-free based servers, we just don't do that properly. Oh, I have a typo, an analogy, not an analogy, an analogy for Unix people. So what an association group is, this looks at file descriptors. A policy handle here is what I call a file descriptor. It's a reference to an object in the kernel. It's a reference to the object on the server side. And the space where this policy handle is valid is a process. That's the Unix process, where this is a file descriptor. The policy handle, likewise, is valid for the association group. And the network connection, I mean, this is our basis so far, is a Unix thread. And so what this means is that policy handles just are valid across network connections, across all threads. File descriptors are valid across all threads. And we just don't do this properly in source 3. This is solved in source 4 by putting our RPC servers that do policy handles into one process, so which is not entirely scalable to the levels that we would like it to scale. Yeah, but so it is solved, but not really in a satisfactory way. How do these association groups work? Clients asked for them, and the server assigns a 32-bit ID. when a client asks, hey, please get me a new association group. Clients then, after this ID has been assigned, later on can reference this association group. And how does this work? What do I have here? It's the bind packet from the previous display of the Wireshark slide, of the Wireshark trace, just looking at the bind packet where the client to server packet says, hey, association group 0. And if you look at this DCRPC spec, the client should set this association group field either to 0 to indicate a new association group or to the known value from previous calls, and so on. So what this means is when the client comes in the bind package, which is always the very first packet of an RPC connection, when it comes with a value of 0, server says, hey, get a new association group. Here's the ID in the acknowledgement PDU packet. How do we solve this here? And this is yet another of Metz's genius ideas. So Samba DCRPCD, what does it do? This, going back one slide again, this packet is always the very first packet in any TCP, named pipe, or whatever RPC connection. And there the client specifies, hey, I want to be part of that association group or get me a new one. And what this DCRPC server then does, it listens on the socket, it accepts the connection, and it reads the first bind packet, the very first packet. And this is really simple to do. You don't need a full-blown DCRPC implementation for that. That's doable in very simple code. And from this, the Samba DCRPCD knows two things. First, yes, this is really server service or LSA or somewhere. Or, hey, this is an association group that the client wants to connect to again. And what the parent now has to do is it needs to find the correct daemon that is responsible for this particular association group. And it took like 2 hours of call with Metze to understand his idea and to implement. Implementing it was another few hours. Metze's idea was now, we will never have more than 256 RPC daemons processing winreg or SAMR requests. So let's take 8 of these 32-bit association group IDs and let's use them as a process index. This means that the parent can look at the association group ID that the client requested and sees, hey, this is process 0, 1, 2, 200. This is what the client requested. And this is the way that the Samba DCRPCD knows which of its helper daemons, RPCD winreg, RPCD SAMR, and so on, this needs to be sent to. And yeah, what the parent then does is it sends the socket connection, together with the bind packet, just as a raw blob to the RPCD helper. And yeah, then the RPCD helper already has the bind and can just continue processing it as if it just had read that from the socket. So if you look at the patch, then you will see that we now do association groups also in Samba 3 properly. And this is kind of the end of my talk. And I got 5 minutes left.
Volker, it's Jeremy here. Wow, I learned a lot. Yes, I didn't know about the association groups. I didn't know what they were. That was very cool. I do have a question. In server service, there are some really ugly calls, get file security, set file security, which were put in there for Windows 95 clients, and they involve smbd type things. How did you solve that problem for the linking issue? Or did you just, the other thing I was wondering is, can we just start returning not implemented for those, please? Because I want to get rid of them too.
good question. I mean, right now this is kind of fake because I link smbd base into all these. So we have access in the RPC daemons. We have access to everything right now. And I want to split on, and this is where my question to Andreas in the talk yesterday came from. I really want to trim down the Samba DC RPCD to really the bare minimum, just because this is an on-demand daemon that we need to be able to start up very, very quickly. For the helpers, I mean, if you have server service and you need these calls, if you have workstation service to list files, yes, we need the locking, we need all the smbx of open global stuff. We need a lot of stuff, but we have a chance now to split these up. And one of the reasons why I also did this was this would be a basis for NumJ to actually do good RPC services if we have split that out.
Yeah, that's a really great point. Thanks very much for answering that. Yes, and like I say, I learned a great deal.
And I mean, NumJ's list of open files will certainly look different, but all he has to do is just implement a different RPCD_workstation service. Just drop it into the libxx Samba or wherever, just replace it with what we have, and let him look at his structures, using our PIDL, using everything. What I've not done yet is look at the source for RPC servers. So let's look at, are there any real questions in the chat? Günther, now wondering how NCA CN IP TCP-based service. Yeah, okay, that answers it. Günther, speak up. Just unmute yourself.
Ralph has also asked, when can we have it?
Yeah, the problem is the following. Let me just share the other screen again. Oops, wrong. That's the big one. And this is the one I wasn't able to split up again, to split up properly yet. I mean, I wasn't able to really split that up in a sane manner. And yeah, somebody needs to go through this and understand 1,434 lines of really subtle stuff.
Hey, that's not so bad. If you look at the VFS changes, that's a drop in the ocean. or even the changes that had to go into the name lookups for the DNS. That's not so bad.
Yeah, well. What will the performance look like when remote WinSpool calls into spoolss calls into winreg? To be honest, I don't know. I mean, this is pretty much what we do these days anyway, just in a single process. We marshal, unmarshal, and so on. I can only hope that the Unix transport that goes in between doesn't make it much worse. So I haven't really done any performance here. But essentially, I mean, I believe that most of the performance that we lose is the marshalling and unmarshalling, which we do right now. I mean, for no good reason, but we do it right now.